today, as I promised yesterday, I still had some general and relatively abstract matters, but I think it's time to move to something a little bit more specific and concrete, if not practical. So today I would like to illustrate, again, always without going too much in detail, but to give you a sense for a specific application in which one would. The example is basically microfluidics and nanofluidics, where out of the 4 levels of the hierarchy, which we have been seeing over and over again for the previous 2 days, we will basically work as the highest level, means a continuum fluid, and the 3rd level, which is the level of classical atoms, classical molecules, so basically Newton, Stokes, Navier. Okay, in general, let me switch it. In general, there are many reasons why you may want to question, in fact, continuum mechanics for a micro or nano flow. Suppose you have a situation like this, and this is a channel. Eventually, you have some obstacles, in this case, the thin plate, which would eventually develop a rather complicated flow structure. And the question is, how small has this channel to be before you start questioning the continuum picture? And that depends on the physics, but it is generally understood that when you go below, say, in the order of the micron or less, then it's not obvious that you can use the Navier-Stokes fluid equation, especially near the walls, which is where, in fact, the discrete particle effects, the granular nature of matter, starts to give effects which are, in fact, generally not included by the Navier-Stokes equation. In particular, if you go to microfluidics, which, as you know, is a very hot subject today, there are many, many applications, especially in connection with biology, where you want to move fluids across thin channels. Thin means of the order of micron or 10 microns, sometimes sub-micron. And there is a very basic barrier that you have to face according to fluid dynamics. It's really a simple calculation. If you take the Navier-Stokes equation and you drop the inertia, U is the average velocity of the fluid, and so if the fluid is moving slowly, as it does normally in a, say, millimeter per second or even less, you can generally drop the inertial term, the one we discussed yesterday and the day before. This is responsible for turbulence. In principle, here we are not talking turbulence, but we are talking a different kind of physics where basically the competition is between pressure. So generally there is a pressure gradient across this channel and dissipation. Okay, this is viscosity and this is Laplace operator. So the competition is between these two, and it so happens that if you solve this equation under static conditions, so you say that you are at a steady state, you drop the time derivative, you would immediately derive, and you can see that even on dimensional arguments, that the amount of the mass flow rate, which is to say the amount of mass that you can push through this channel in the unit time, goes, of course, is proportional to the driver, the pressure gradient across the channel. It's inversely proportional to the viscosity, because if the fluid is very viscous, there is less flow. But what I would like to bring to your attention is this power h, power 4 of h, where h is the channel length. The channel width. And if you think a moment, this is a very steep barrier because actually this, the point is that when you, I think this is wrong because it should -4. Yes, I apologize. I didn't mean to trip you up. But actually, I got this for one of my brightest collaborators ever. I should really complain with him. This is from Maurus Bragari. Anyway, so this is -4. The reason is that, and you see that if you take the dimensionality properly. So the message is that if you make your channel twice thinner, in order to get the same amount of flow rate, you have to push 16 times stronger. Okay? And this 4 actually comes from the combination of 2 effects. On the one side, there is the fact that the flow rate is proportional to the area. Okay? Because this is the amount of mass which is flowing through across this rectangle area. as combined with the curvature, because the Laplace is 1 over length square. So the two things combine together and produce an exponent 4, which is terrible. I mean, as I say, if you have to go down by a factor 10, in principle, you have to push 10,000 times stronger. So it's very hard to push fluid into small devices. Of course, however, this is not necessarily, not of course, but people realize that this very unfavorable scaling derives from the fact that you assume that on the walls, this is the solid wall, there is no relative motion between the fluid molecules and the solid molecules. It's called the non-slip boundary condition, which is almost a postulate of continuum mechanics. But as a matter of fact, there is no fundamental principle which imposes this condition. It has been highly debated, and in particular in the recent years, there are several instances where people do observe a slip on the wall. I don't know whether you can see that, but essentially this will be the parabolic profile that you derive from this Stokes equation with a zero velocity boundary condition on the plate. But what people observe is that there is a residual slip velocity, and this is very important because as soon as you allow the fluid to slip on the wall, then you can considerably soften this steep barrier. So there is really huge technological interest in inventing tricks to allow the microfluid or the nanofluid to slip over the walls. And you surely appreciate that this really depends on the details of the interaction between the fluid and the material on the solid wall.
Also the viscosity between nanofluidics drops, so that helps also the effect.
Yes, well, nanofluidics and microfluidics are not exactly the same in this, but you're right. In this case, I would all I wanted to say is that there are solid physical reasons why you may want to question the continuum picture, especially near the wall, where is the region where interesting things generally happen. Okay, and as I said, this is highly debated. You go in the classical textbook, and people like Batchelor says that it is now widely accepted that there is no slip on the walls, but then you look into other, there are many papers where they show that in fact there is slip, and I think Maxwell himself was concerned with the problem, and he proposed some extension, in fact, of the Navier-Stokes equation where he would take into account this slip effect. I think in general for polymer melts, for complex fluids, not simple fluids, but for complex fluids now there are plenty of experimental evidence that there is slip on the wall. And very often people try to generate slip on the walls. There is the famous Fakir effect. I don't know whether, I think it's the lotus flower. By some rather sophisticated effect, it turns out that under certain conditions, if you put microcorrugation on a surface, you can generate a sort of phase transition. You generate kind of vapor between the corrugation, and the rest of the fluid can just slide over. So by corrugating the surface, you slip more. And nature makes a heavy use of this. It's called super hydrophobicity. But anyway, this is not a lecture on microfluids. It's just to say that it is a problem where the plain use of continuum mechanics would not do. So again, as I said, you are at this level, and we forget about Boltzmann for the time being. We will come back to Boltzmann, of course, tomorrow, maybe when we talk turbulence. So now, as a specific example, I will take the example of a two fluids. So you have, for instance, many applications. You have a fluid, say liquid, making its way through another fluid, which is maybe air, and this is called capillary imbibition. So in many applications, you need to push the fluid through a small channel. And as I said before, if you abide by the continuum laws, you run into a paradox, which is sometimes called the Heracles paradox. The paradox being that the shear, so we discussed the shear yesterday, the shear, according to continuum mechanics, at the contact point, this is the separation line, this is the interface between fluid A, say between water and vapor. And if you take continuum picture, in this point, in fact, you have 1 over r divergence, so the shear gets infinite. And so it would even Heracles would not be able to push the fluid. That's why it's called Heracles paradox. It takes an infinite amount of strength to move the fluid, but as a matter, so the fluid shouldn't move according to continuum mechanics, period. And in fact, the fluid does move, so the question is why? What happens here? And of course, what happens here is that you cannot use the continuum equation. Just for the notation, this is the capillary force, this is the surface tension, so it's a sort of a force which is experienced by the particles which are sitting just on the interface, and this cos theta is called a contact angle, which is a measure of the effect of the interaction energy between the fluid A, fluid B, and the solid. And H is, again, the width of the channel. So there is a region where continuum mechanics is not holding for sure. And, well, just a movie from a simulation. As I said, in technology there are, people are trying to put corrugation and understand under which condition this corrugation would, rather than hindering the motion, favor the motion. And that's not easy. It's a tough technological problem. Okay. So now to the equations. You remember yesterday I had very rapidly, I think I still have it. No, I forgot to put it. Okay, let me go back. That doesn't really matter. I had a picture where at the level, well, I showed today, the Navier-Stokes and the microfluidics. So we need, essentially, if you want to put up the multi-scale procedure, we need a macroscopic solver. We will need a projector from the, we will need, in fact, a microscopic solver, a macroscopic solver, and the two will run into along two parallel timelines, and from every now and then they have to exchange information. So for the macroscopic fluid, essentially, we use the conservation equation. So that's a continuity, so the time derivative of the mass is driven by the divergence of the flow, and the flow is density times fluid speed. I really don't want to discuss that in any detail. It is basically conservation law, and the time, the evolution of the fluid speed is driven by the pressure tensor, which in general contains some advective component, inertia component, plus, if it's an ideal gas, the ordinary pressure, but this can be a more complicated function. For an ideal gas would not be linear in the density. And if you want to take into account heat transfer, you have more complicated terms. Now, the point I want to make is that here I write 0, but as a matter of fact, there are important non-ideal effects associated with the non-equilibrium, the thing we were discussing yesterday. As soon as your fluid is not totally homogeneous, there are dissipation phenomena which take place, and these dissipation phenomena, in fact, can be traced back to the non-equilibrium component of the pressure tensor, which is just more than this expression. Okay? So in general, what you do, you write this equation would be Euler equation, which is fluid without dissipation, if P happen to be just the sum of inertia and pressure. But since there is non-equilibrium, generally you bring something on the right-hand side, and that something is the Laplace operator. I'm not asking you to prove this, but just to provide you the picture. So non-equilibrium equal dissipation. And I will comment more on that. So much for the macroscopic level. At the microscopic level, we shall be using molecular dynamics, and I don't think I need to comment much on this point. Let me comment a little bit more on this equivalence between non-equilibrium and dissipation, because I feel it belongs to the general notion which can be useful no matter which field of application you're in. Is that obvious that non-equilibrium associated with dissipation? I don't think so. Would you agree that the two words are not necessarily, am I making a correct assumption? Because if this is trivial, I would not spend time on that. Should I come? Okay. So let's take the Boltzmann perspective, because that's the most natural to discuss this connection. In general, F is the probability of having a molecule at a given position, at a given time instant, with a given velocity. So the molecules can move under any direction. And in general, at equilibrium, there is a specific form that this distribution takes. And the form is the very well-known Gaussian distribution, right? So if I have a molecule, V is the molecular speed, and if I'm in a macroscopic media which is moving at velocity u, that of course does not mean that all molecules are moving at the same speed. There is a spread in the distribution. This spread is the temperature. In particular, in this room, the U would be, have you a guess for what would be U in this room? Here. This is the fluid speed. So take a centimeter cube of air in this room. The macroscopic speed is basically 0. It's basically 0 because we don't see any wind gust, okay? But does this mean that the molecules here are standing still and sleeping? No. Actually, they move pretty fast. I mean, the average, this speed here, the variance is about the sound speed. So here we have little guys moving like about 300 meters per second this way and that way, and they just compensate.
Do they actually move faster than the order of 1,000 meters?
Well, in an ideal gas, I think the sound speed is basically the temperature. If I'm not wrong, the sound speed in air is about 300. In water is about 1,000.
Yeah, I mean, you read about the sound, the speed of the sound, but I'm not sure that that's the right estimate.
For an ideal gas, only for an ideal gas. But anyway, the point is that even if you are in a situation where the fluid doesn't move, the underlying word, there is a lot of motion, okay? It's the old cows, right? Democritus, atoms, etc. Okay, of course, if you are if you are freezing outside, this Gaussian would be narrower, and if you go to to Africa, this Gaussian will be broader, so that depends on the temperature, but essentially, just to say that there is a distribution of molecular speed. But if you are close to equilibrium, equilibrium means that if this is the velocity, say, in this point, then I move a little bit, I move maybe half a meter rightwards, and I find basically the same macroscopic velocity. So if this is the case, so if there is no inhomogeneity, indeed, the actual distribution of the molecule will be basically Maxwellian. But since this flow field, or for that matter, the temperature, as soon as I develop some space dependence, as I move to the next point in space, maybe I will find a different, slightly different distribution, which is the one I indicate here in red, because there is some departure from the Gaussian shape, which is red minus black, which is normally the non-equilibrium component of the distribution. Now, it takes really the back of the envelope to show that to first order, the non-equilibrium is basically the mean free path, I'll tell you in a moment what this is, times the gradient of the equilibrium distribution function, which is the mean free path times the gradient of the velocity. So in other words, inhomogeneity feeds non-equilibrium. And there is a number which measures this departure. It's called Knudsen number, which is essentially the ratio of the two. And if you want to be safe into hydrodynamics, you better make sure that this Knudsen number is small. For a decent fluid, this has to be less than 1%. So what is this mean free path? Just an illustration. Suppose this is the density of the fluid or the macroscopic speed, so a macrodynamic observable. And suppose you have this kind of trend. So there is a smooth variation over space scale capital L. The mean free path lambda is in fact the distance traveled by a molecule before it meets with another molecule. So I have a molecule here moving perhaps straight, and at this point it meets with another molecule, and it makes an hardcore collision, and time and again. So in order for hydrodynamics to hold, this distance has to be much smaller than this one. So there has to be scale separation. Okay? And if this is not the case, like in microfluidics very often, then hydrodynamics goes under question. Is everything clear at this point? Okay. So coming back to, I think I don't need to make any further comment. This is too detailed. So now what happens, in fact, where we are not under the condition of weak departure from local equilibrium? So that will be the condition we have been discussing. And please, another point I would like to make, viscosity is not given by God. Viscosity is a property which makes sense only, strictly speaking, only under a weak non-equilibrium. And for instance, for an ideal gas, typically the viscosity, which is a length square over time, is of the order of magnitude of the thermal speed of the particle, the one I was showing you before, times the mean free path. Length times velocity. Okay? This is the kinematic viscosity, centimeters squared per second. So under ordinary conditions, you say this water has, air has a viscosity of 10 to minus 6 meters per second, water has another viscosity, etc., etc. And you consider that a property of the fluid, which is correct as long as the fluid is under equilibrium. In many, many applications, including the blood rheology, this is not necessarily true, and actually also because the internal structure of the fluid makes a difference. So what people tend to do is to let this viscosity depend on the amount of shear. In solid state, you learn that if you put the stress, which I don't know whether you can read it. This is called tau, and a deformation follows. So you have an undeformed piece of fluid like this, then you put it under shear, and you see that there is a deformation like this, and this is what is indicated as the shear rate, gamma dot. So it's a measure of deformation. And normally you would say that the two go together, and the constant in between is the dynamic viscosity of the fluid. Now, if this shear becomes stronger, eventually the model develops a nonlinear dependence on the shear itself, and so there are a series of rheological constitutive relations where the viscosity depends, in fact, on how much you are shearing your fluids. But that's good enough, but if you're really wildly into the region of non-equilibrium, what happens is that even this picture is not sufficient, and basically viscosity becomes, in mathematical terms, it becomes a totally non-local operator, and that is the point where, in fact, it doesn't really make any much sense anymore as a physical variable. These are the point where, in fact, it is just too complicated to be useful. Okay? So, of course, you can try to do that, and there are people who are writing equations for dense fluids. I once saw it in a paper. I wanted to take a copy of this but to show it in the seminar. It's just 3 pages crammed with equation. I mean, it's a sequence of 3 pages with equation, equation, equation again, just to take into account all the terms associated with this expansion. It's just like having Feynman diagrams up to level, say, 20 or something like that, which really look very daunting. So what we are trying to do, as I was saying yesterday, is to take a different perspective, and instead of trying to find the correct equation when the viscosity becomes a nonlinear and integral operator, you try to combine 2 different numerical methods. So essentially, you want to do FH stands for fluctuating hydrodynamics. Never mind. So the idea would be that for a certain region, you use fluid dynamics. Suppose here you have the wall. So away from the wall, you say continuum is safe. But close to the wall, then I need a better description. And maybe I will use molecular dynamics. And there will be some interface in between. The idea is the following. Sorry for the notation. This is the shear, and this is the stress. That's what in the previous slide was called tau. So instead of using, so this is the macroscopic flow, and this is the deformation. Okay? So this is the shear, and this is the stress. Instead of assuming that the fluid obeys such linear relation, or eventually with mu, which depends on S, if you want to allow for nonlinear extension, you would try to feed the shear directly from molecular dynamics. We don't need to go through that, but essentially you can compute the equivalent of the shear using the definition of using the particle velocity, and this is nothing but the potential energy. So Rij would be the distance between 2 molecules I and J, and Fij would be the force experienced by this pair of molecules. If you are in a molecular dynamic situation, in principle you can measure that. Maybe you do some time averaging, but you can compute this object, so to say, ab initio, without making any assumption on whether there is a relation between the strain and the shear. So you can feed the constitutive relation as you get it from a microscopic level, which is supposed to capture the correct physics. So the idea is use continuum for most of the region, but near the wall you want to be a little bit more fundamental. And of course, you have to make sure you couple things correctly. And that is the picture I was showing yesterday. So, well, that depends where you start. For some reason here I start from, let me see, micro to macro. So I start from here. I take a microscopic configuration, I project it into a macroscopic one, then I advance the macro solver for a stretch capital delta T, then I project back to the micro, okay, and then I will advance the micro and so on and so forth. Of course, as we discussed yesterday, nobody really tells you in advance how long should the red strip be and how long should the green stitch be. So it's kind of heart that you need to put into your scheme. I'm speaking a little bit more. Any question at this point?
Yeah. That projection from a macro system down to some micro state, there are zillions of microstates for any one macro state. How do you pick one? How do you do that step?
Pardon? There are zillions of...
Yes, when you're going from the macro down to the micro.
Ah.
And it's not straightforward to me how you...
No, it's not straightforward to anybody. You are in good company. No, I was saying, that's precisely, we were discussing this in abstract term in the first lecture. This is exactly the point where you are losing information, no question. And the best you can hope is to retrieve the maximum amount of information you can, but that's an intrinsic, there is a sort of uncertainty principle. That's the way we call it. There you lose information. That's a price you have to pay, no question. So you are right to the point. Here, no. Here you project, so here you destroy information, right? And often you destroy information you don't need. But you know to make a mistake, and here you try to recover your mistake, but you have to live with errors. It's like real life. You have to live with some frustration, but you try to minimize it somehow. So it's really a more realistic way of...
Do you project to only one microstate, or in practical terms would you go and let's say run 10 or 20 micro MDs in parallel and average over that?
That's again a good point. To the best of my knowledge, people who play this game, including ourselves, although we don't play exactly this, do not do much ensemble averaging, so averaging over trajectory. Typically, they do a lot of time averaging, hoping that the two things are the same, which is true if the system is ergodic. But you don't know whether the system is ergodic. In fact, I think ergodicity has been proven for maybe 2 or 3 systems. I think the billiard ball, the billiard by Sinai. Normally, you assume it is ergodic, but there is no rigorous proof. But in practice, people average in time. That's what they do.
I think a delicate part that was probably raised because when you project down to the microstate, you want to pick a state that is consistent with the statistical state.
Yeah.
And out of equilibrium, you have no knowledge about it.
Absolutely, we will come to that. We will definitely come to that. Absolutely, absolutely. That's really the crux.
Yeah.
Absolutely. No, we will come to that. Absolutely. This is the delicate part. That's the whole story, basically. No, actually, there are important technical features here. Whenever you have to change level, you have to be careful with the interfaces, so-called handshaking. That's technical and very important. But here there is something fundamental, because you have really to reconstruct information which has been destroyed before.
Well, I mean, hopefully, what you're propagating in the red strip is degrees of freedom that account for major changes. And the degrees of freedom that you have discarded in this arrow don't really matter. So you basically plug those in, and as long as they're consistent, the microstate is consistent, it shouldn't matter. It should be a representative state.
That's right, but you're kind of closing your eyes.
All right. I mean,
You hope that when you open them back, you're still safe. But in general, that's exactly the point. I mean.
Well, I mean, that's sort of part of the design of what are the important degrees of freedom to propagate in the red strip and what are the ones that
Absolutely,
we can afford
absolutely. You remember yesterday, for the previous 2 days, I was always been using this very simple notation, small x, capital X plus fluctuation, but this is really a simplification. In real system, it's not really obvious to know who is the capital X, and the fast and the slow, when you have, say, a protein or some, what are but I think there people inject their knowledge.
Yes, exactly. That's where you inject.
No, I think this, it's a big difference if in the red strip you're using, say, Navier-Stokes,
Yes.
where you have no information about the statistical features. And so when you want to go down to the microstate, you have to make a guess. That is
You have to know some underlying
Yeah.
physics.
If you use for the red strip, say, lattice Boltzmann, where you have statistical
Yes.
distribution, then life is easier. So it's really
Oh,
a way of,
now you're, yeah.
Yes.
because you have a guess, or at least you can obey a principle.
But people don't do that. I mean, we are the only ones.
Yeah, I mean, right. I mean, that's also
No, that's the point.
part of the choice of what
That's part of the choice.
method you use for the red
Absolutely.
strip.
That's why I always insisted, even last year, that especially the young people here, always keep in mind the hierarchy. Be always ready to use the most useful drawing into this because not to criticize, but generally as a mechanical engineer, you would be trained that continuum mechanics, Navier-Stokes, period. There is nothing else. There is a whole world behind, below actually. And if you are aware of that, then you can make your choice. And I think engineers, I don't know in this country, but they now start to get exposed to statistical mechanics, precisely for this reason. The nano engineers, at least, micro nano engineers, they really need to know about statistical mechanics. Whereas once upon a time, and I think in Italy still very, very much behind, they would just do macroscopic thing. Conservation law, that's it. So, yeah, but all what you have been commenting is absolutely correct, and I think I'm coming to that later on. So, a little bit more specific, not much, but a little bit. So, suppose we have our channel, and what we would typically do, we would integrate, and well, actually, this is not a very good example, but anyway, let's assume that there is something critical here. I mean, it should be actually only one stripe if I put a wall, but let's say that you have some reason to assume that there is a strong heterogeneity in this region, and so in this region you want to put a stitch where you use molecular dynamics. So blue is molecular dynamics, and this is the continuum. So of course there are certain technical aspects that you have to take care of. For instance, if you are here, you are integrating continuum fields, so density or velocity, and normally these live on a grid like that. So the white ones would be sites where I store fluid information. And when it comes to the interface, of course, I have to move this information into molecules, which in principle are grid-free. The molecules can live anywhere. Okay, so and this normally you would have to do interpolation and the standard tools of the trade. And on the other side, when you move information back from the micro to the macro, this is sometimes called gather, because you are gathering information from the grid, and here you are scattering it back. Okay, so these are technicalities, but they really do matter when it comes to implement, and they would affect the quality of your results. This is space. But of course, you have also to take care of time, and typically, as we were discussing yesterday, you, in order to gain, you remember the gain-pain factor, you want to have some separation between the time steps, so that means that you will have a, here I'm using lattice Boltzmann because that's what we did for our polymers, but this will be the continuum time, so Navier-Stokes or macroscopic time. So in macroscopic time, you will have big time steps, and you would, so for instance, you would get, say, by projection, you would get from a microstate here the macrostate, they make delta t, and then you give it back. This is not a good example because there should be no small, let me put it this way. Let's consider this. You start from a macrostate and you advance, and then you project it here. And here, of course, you want to advance in smaller steps. And typically, this separation, in our case, we are very aggressive, I think. We are taking literally a factor 5, but in general, when you couple Navier-Stokes and molecular dynamics, these are hundreds. The reason why we are taking 5 is because precisely what Simone was commenting. Since we are using lattice Boltzmann instead of Navier-Stokes to do macro fluids, but since lattice Boltzmann is kinetic theory, it is kind of closer to molecular dynamics. So we were hoping that we can couple them a little bit more tightly. But nevertheless, this is just to mention the fact that the timeline in the microscopic timeline and the macroscopic timeline advance in different time steps. So you have to exchange information not at every single time step, but only every now and then. Otherwise, it would be too expensive. What is this? Oh, that's a bit thick, but actually it's simple. So remember what we are doing. So we are doing, let me see if I picked up the right sequence. So the first step I want to do micro to macro, okay? So micro to macro and advanced macro. Okay, so it should be like that. Micro to macro. Conceptually, it's very simple. So I now have all my, I just use the position and I indicate the position of the particle x sub I is the particle index at time t. So this is the particle trajectory. If I want to build a field out of this particle, so I want to know the density of my fluid, all I have to do is to define a box or a grid point. Let's use this. This is the grid points where I store the density or the current, all the macroscopic fields, and I have particles moving up and down. So all I have to do is to say, okay, I define a box, and I want to count, literally, how many particles are falling within that box. That's what this notation means. So I belong into the box centered in X. Of course, there are different ways of defining the box, and again, you have really to be very careful with these details. But conceptually, it's simple. I'm just collecting. For instance, typically what you would do if I have a particle here, I might give 1/4 here, 1/4 here, etc., etc. Or you may split the particle in a more sophisticated way, but essentially you are moving the information from a grid-free location to the grid location where the fluid is defined. So that is the projection. And when it comes to the tensor, it's more complicated, but I don't want to comment on that. So I think this in principle is very crystal clear what you have to do. Then you evolve, and that's the standard method. I mean, I don't even bother here to comment the scheme, but essentially you would have a finite difference grid, and the time step n+1, this will be a macroscopic time step. You have a time derivative, and you put it into discrete form like that. You will have a current divergence, so you have a delta x, and here eventually you have a flux. So that is, here you can use any of the zillion of possible methods of computational fluid dynamics. In our case, we use lattice-Boltzmann, but that is not relevant at this point. What matters is that away from the region where you want to use the molecular dynamics, you know how to move, how to advance your information. FD now stands for fluid dynamics. I'm sorry, I keep changing the notation. So you advance your system, but at the interface, you want to move the information now to reconstruct the information and move the microsolver. How do you do that? And this is the delicate point. There are two steps. One you have already commented. So once we are in a grid, we need a kernel which transfers information from the grid to the particle, which is what I commented before. That would be interpolation, extrapolation. So that is standard. But when you need the further step, which is very important, because you have now to construct the microscopic state. And as Simone was pointing out, when what I indicate here with phi, this is phi living on a grid location, and this could be the density, this could be the pressure or the fluid speed, but certainly has no information on the molecular degrees of freedom. And that you have to postulate. So what you do, basically in practice, suppose you have a cell, it's pretty decorated, I will tell you later what the decoration is. But basically in a cell, you have where you know from the macro solver that you have a density rho. The cell is a given volume, a given temperature, a given velocity, and a given shear. Then you have to insert.
Where's the temperature coming from?
Well, the temperature eventually will be one of the, depends on your problem. Normally in a thermal problem, you would advance density, pressure, flow, and temperature. So that is part of the set of macroscopic variables. It would be, now I indicate just rho and j, but I would have other equation like that. I would have the derivative of j, as many as you need for your problem. But the crucial point is that no matter what, this will be a field living on the grid. Okay? And there is no notion whatsoever of the microscopic world. So here you have to sample. Sample means that you have to insert a certain number of particles. You know the number because you have rho from the macroscopic state. You have the volume of your cell, and you know what the mass of your particles is. So you have to insert a certain number of particles. Typically, you do this at random location within the cell. So suppose that you have, say, the temperature here, or the density. The density is the most intuitive. And you know that you have to insert 5 particles into this cell. Okay, how do you do that? Well, normally, as far as I know, from the spatial point of view, you just take random location within the cell. So, and you put, because it is assumed that it will really doesn't really matter whether the particle is here or there. This is basically the resolution of your calculation is basically the size of this cell. But for the velocity, it's more delicate because you have to give I should have put an arrow here, which I forgot. It was there. I didn't hold it. I should have put an arrow here because here I have to initialize not only the position but also the molecular speed. How do I do? Well, if I can assume, if double F, that I'm at equilibrium, I will sample from a Gaussian. I will do G rand of something, and I will get back my speed. Actually, that's a practical, for practical purposes, normally you work with the so-called peculiar speed, which is this relative speed. This is the molecular speed minus the flow speed, which I have in the grid, normalized to the temperature. That's what you would get typically from a random number generator. And then, since you know the temperature and you know the speed, you can immediately reconstruct the velocity. So that's the operation on the Maxwell distribution. But I just insisted a lot that we are doing this game because we are out of equilibrium. So in a way, we are defeating the whole purpose if we sample from. I could sample from the Maxwellian. Suppose I have my critical stuff here, okay? And this is where I need molecular dynamics. And I do molecular dynamics, and I have to solve all over the table, okay? If I do molecular dynamics for half of the table, the interface will be at equilibrium. But by that time, I've been ending up using molecular dynamics as an overkill. So I would not gain anything. What I mean is the following. If I make this blue strip very wide, of course, the interface will be further and further away from the critical region. And then sampling from a Maxwellian would be probably OK. But the price to pay is that I have to use a very extended region of molecular dynamics, which is precisely what I do not want to do. So it is clear that there is a trade-off. On the other hand, if I get very aggressive and I want to use just a little bit of molecular dynamics there where it's really badly needed, then I have to accept the interface is not at equilibrium. And then, who tells me? Probably if I sample for the Maxwellian, I just lose all the important detail regarding non-equilibrium dissipation that I want to capture. So you see why, again, it's an art. And I will stop here because this is really the most important. So if this is clear, I would go on. If not, please ask questions. You tell me when we want to have the break.
You have a question?
Yeah.
Yes, I'm not sure I know how to formulate it.
No, please. We are here just to discuss.
We're working with these cells individually, which is saying that any information about variations or fluctuations at a scale larger than those cells has been captured in when you define the cells. That is, you're saying you know that the density in this cell is such that there should be 5 particles
That's
in that
right.
particular cell.
That's right.
Okay.
That's
So,
right.
and the adjacent cell might have a different density.
Oh, yeah, sure, sure, sure.
Okay.
What we are assuming is that the size of this cell will be small as compared to the variation of the density field.
Okay.
Okay? But it will not be small as compared to the density. But in general, there will be fluctuation. If I represent the density associated with the particle, I'm sorry I don't have a picture, I will have, and when you do the simulation, you definitely have the density, which you basically average by doing time averaging. But if I show you an instant snapshot of the density as given by the blue particle, it will be highly fluctuating, but you average out. Okay. But of course, you are definitely right. If I put another cell next to it, the density in the next cell would be in principle different, but not that different. Because if it is very different, then I have trouble with the macro solver.
Yes, and you then have a boundary.
Yeah, I'm not doing my job properly on the macroscopic equation. Here I have to do 2 jobs, actually more than 2. I have to do a good job solving macro, solving micro, and matching them.
Yes.
But coming back to Simone's point, I mean, that's technical. It's a very important technicality, but here it's not technicality. Here you have to somehow invent. And of course, you're using your knowledge of statistical mechanics. And as I was saying before, people accept that, and here we go into really the hardcore, people accept that an equilibrium distribution function would not be appropriate if you're just working close to the critical region. What do you do? Well, you do your best. I mean, yeah, I showed you before that hydrodynamics holds in the limit where the mean free path times the gradient is sufficiently small. So to a first order, at least, you could say, okay, I do not want to sample for Maxwell. This would be Maxwell distribution, which only depends on this peculiar speed. Okay? And I will correct with the gradient. So I can take the gradient of Maxwell, and gradient of Maxwell will immediately go into a gradient of u and t. So I will pick up information from the neighborhood. Okay? And then how about sampling from this? Now there is a potential problem with this simple move, and I would really be happy to get it from the audience. Or to what problem do you see with? Remember, if I can give you a clue, yesterday we talked about realizability. You want to do things, but you don't want to break fundamental constraint. There is one very fundamental constraint on a probability distribution function. Hopefully it should be greater than 0. If it is not, you're doing poorly. Okay? Well, eventually you can survive. But
Even with negative probabilities, well, you may eventually can survive.
if the real problem is that not that getting just an instantaneous negative value, but when it persists. Sometimes the code can cure itself. If you just go negative a little bit, you can reemerge sometimes. But it's not advisable to work with negative probability. So when I sample from a Maxwell, there is no question that Maxwell is positive everywhere. But as soon as I take this gradient, and if this gradient is strong, in principle, it could spoil the positivity of the, especially, I mean, if you are really far off equilibrium, in principle, you have to sample, you might pick up a rare event which brings you negative. Now, sampling from a non-equilibrium distribution, as far as I know, is still an open technical issue. There are people who publish beautiful papers just devoted to this issue.
Can you have on that, let's say, if you increase your cell, and look at this function again.
Which function? This one?
I mean,
which function?
Or the gradient. I mean,
this one.
Because I'm thinking of that you have these cells, and you have not just one cell, I guess you have many cells.
I have many cells, yes.
And you have to also take care about the how consistent, at least in the neighbor cells, and your distribution function should not deviate too much from cell to cell, I guess. I don't know, but
no, you're right. In fact, that's precisely the point. I mean, when I take this gradient, if this gradient is a macro operation, because the gradient we pick up, look here, I take the gradient of Maxwell, okay, a spatial gradient. So actually what I'm doing, I'm taking the gradient of the velocity and the temperature. So I need to compute the velocity here and the velocity in the neighboring cell. So I need to get this information from the macro solver. Now, hopefully, this gradient is still relatively smooth, so that this will be a small perturbation. And this is generally the case, frankly speaking. But if I am really in a super shock, say I'm doing shock propagation in combustion or aerodynamics, if you're just pinning down the shock, this quantity will be 1. So what I'm saying is that that doesn't happen for microfluidics, by the way. It's very rare. So I'm kind of exaggerating. But the philosophy is that this quantity should be a correction to 1. If it is a correction to 1, then you're fine. If it is just a small correction, the chance of getting a negative event is very negligible. And I was told by people who do that for a profession that when they pick up a negative number, Alejandro Garcia is one, I would say is the word expert. So he says that really rarely, it does rarefied gas dynamics. That happens very rarely, and when it happens, you just say, okay, I throw around another random number until you get it positive. And it says nothing really terrible happened. There is another field which is probably of more interest to you, is the Wigner distribution function. When people try to do semi-classical computation, and Wigner distribution is not positive definite, right, physically. And again, when they have to sample from Wigner, eventually they would pick up from time to time negative values, but these negative values really don't affect much the observables. So they can live with mildly negative distribution functions. I heard that by, I think it was Ray Capral, some people who do semi-classical computation. Just to say that F negative is not really a taboo, but is, I mean, it's a red lamp, okay? So you shouldn't.
Like something that was a kind of trivia in the beginning, but it's not.
Please.
This picture, especially for the spatial distribution, looks very simple if the underlying fluid, the particles, the blue particles, are ideal.
Ah,
As soon as you have a real fluid, this becomes extremely challenging for a number of reasons.
if they have a structure, you mean?
If they have interactions, the particles have interactions. Imagine that P now comes from the equation state that comes from Navier-Stokes and whatever.
Right, right.
Now you want to accommodate blue particles with a given density and a given pressure, and these particles interact. This is already very challenging.
Oh yes, because I will counter, because you have to do constrained molecular dynamics.
Well, just picking the right state is challenging. But in this case, you're still doing a mean field because the equation state has no information about correlation. Now, if you have correlation, spatial correlations between
Spatial correlation between whom, sorry?
particles, you have a radial distribution function you have to satisfy, this becomes still more challenging.
It's the next slide.
Then
It's the next
third
slide.
difficulty, if you have now a non-equilibrium state,
Yes.
you have no more separability between velocities and conformation.
You have no more, sorry?
Separability between the Maxwellian, there is no more separability between position distribution and velocity distribution. Then
You don't
third
know where
level-
to sample from.
third level of difficulty. So
Yeah,
it's
yeah.
really a kind of works.
Oh, yeah. Sure.
So it's not trivial. I mean, in principle,
No.
yes, you have this
No,
this
it is
option.
not trivial at all. I mean, sampling for a liquid is highly not trivial. I totally agree.
Another question, maybe you will be coming to this, but
Yeah, please,
how
please.
do you ensure that your non-equilibrium is conserved in your molecular dynamics? Because if you just run an unconstrained molecular dynamics following the forces, you will end up in some kind of equilibrium, which is, I think, precisely what you don't want. So do
That's
you
right.
apply
You-
any kind of constraints or
Yes.
driving forces
I'm
to
not
your
an expert of this, but for sure you do constrained molecular dynamics. It's coming. I'm really not the keen expert on that. I know what's going on, but I mean, no, absolutely. All what you're saying, I mean, I'm trying to convey the zeroth order of a picture, but when you go professionally into it, it's full of non-trivial. I think it's basically still open. I mean, there are 3 or 4 groups in the world working on this, and they don't use the same methods. I think it's still open. But I think some of the points you made, which are certainly correct, I have in the next slides. So what I wanted to say here, just as an aside, it is nonetheless perhaps instructive to know that if you want to be, it is a good practice to locate the macroscopic variables in the proper position. One would think that everything has to be placed in the center, and that's not quite the case. Typically, scalars go in the center. The velocities, for instance, as a vector, the vertical velocity should be stored in the middle of the corresponding edges. So this would be velocity going this way, and this velocity going this way. The horizontal velocity should be stored here and there, and the tensor should be stored in the corners. And it's a technicality, but if you don't do that, you spoil the conservation laws in the lattice. So it's full of really technical subtleties which really matter a lot. So just to say that the continuum variables do not live in the same place. They have to be properly placed. But to the purpose of sampling, I mean, this is basically not important. This is important to do a correct job on the macroscopic side. Now, sampling again, I think this is part of what Simone was saying. This picture applies to rarefied gas, where you have, as I said, say you have a shock wave, and so you can develop very strong gradients. But essentially, the fluid is a simple fluid. It's a gas, actually, argon, or there is no structure, etc. When you go into the liquid, things become more complicated because, as Simone was pointing out, there are correlations. So you cannot really say that what you need is the probability of having a particle at position 1 with velocity 1 and a particle at position 2 and velocity 2. And the two things do not separate, as Simone was pointing out. So Boltzmann, I remind you that Boltzmann is the level of kinetic theory where this part here is forgotten. So the probability of finding particle here is independent of the position of all the other parts. But in a liquid, there are correlations, and they are basically encoded into the so-called pair correlation function, which is In principle, it would be a function also of the velocity, but in practice, the main dependence is on the spatial coordinates. And the typical correlation function for a liquid will look like that, for at least half sphere. So this is the interaction radius, so you don't have, this is the incompressibility constraint. You don't have any other particle within your radius. And this is the probability of finding a particle, a pair of particles just a little bit further than the radius of the R sphere. Just to say that people know more or less how the radial distribution function looks like in material, but I think, and Simone knows better than me, I think there are very, very few instances where this is really known exactly. I think R sphere is a case, and very few others. So I saw papers where people just tabulate. And if the fluid is a complex fluid, I think they have no chance. I mean, you have to tabulate. So here is the point where you try to do your best work, but you are not guaranteed that you are reconstructing the information properly. However, there is a big act of faith into the whole philosophy, which I was mentioning yesterday. And I had even a picture on that. The faith is that by the time you do an error here, but since here supposedly you're working with the right physics, this will heal the errors. Okay, so there is this healing function, which is really something you are postulating.
What you're saying is you're getting closer to equilibrium.
You will make a mistake, but this evolution will basically destroy the error. I had a picture yesterday where I showed that people measure these kind of things a posteriori, and in many instances there is really this healing effect in action. If this healing effect for some reason fails, period, you've lost. So the idea is that I know that I have an error here. I will do my best job to minimize it, but I will not make it to zero. But since I plug in this error back as a perturbation to the correct solver will take care of it for me. So the physics will do the job, even though it will not be me, it will be the physics doing the job, which I like as a philosophy. You know, it's kind of self-correcting. It's like, again, a little bit more like nature. So you make mistake and you correct on them. But you have no theorem for that. Back again to what we were discussing yesterday. You see the very different philosophy. You do not try. It's a bit like Prometheus. You don't try to steal the fire. Just reconstruct everything exactly rigorously. You say, I know that I have my limits, and I let nature do its job for me as much as I can. So I like this philosophy best, but that doesn't really matter much. So, and the third point that Simone was making, I would kindly invite him to bring it over again, because I'm not sure I got it. So you had 3 points. I think 2 of them have been addressed by my, and the other one regarding I think it would be interesting discuss. Well, you mean why you mentioned the equation of state?
If you have a cell,
yes,
it's a closed system, say, you want to sample particles, forget the velocity now,
yes,
just the structure,
yes,
with given density and pressure.
yes.
I don't know how to do it.
Ah, so in the same cell.
The same cell.
Ah.
You want to pick a number of particles, and probably the number of particles must
I
be
see what you
variable,
mean.
must
I
be
see
an
what
open
you mean.
ensemble
I see what you mean.
I mean,
I see what you mean. So you say it's not enough to say, oh, I have NP particles. I place them so that I get the right pressure. You're right.
There can also, I mean, if you have a hard sphere model or something like that, that constraint has to also be observed between cells. You can't have 2 cells right next
The
to
fluxes.
each other across the
Yeah,
cell boundary.
Yeah.
you don't want overlaps or crazy configuration.
Yeah, you're right. I should have an extra point on this. I didn't think of that. Yeah, you're right. So having the 2 together is not trivial if they interact. That's true. That's true. So there are many.
And don't you also have to make sure that your pair correlation is valid between cells? That so you have to. It's not enough to stay within a cell and have those particles correlating correctly there. Then you have to take all surrounding within cells.
Yes. I think that, frankly speaking, I would not be able to go into the details, but I know that people care a lot about securing the continuity of the fluxes.
How large in practice are your cells compared to the MD? Do you have, how many particles do you have?
Basically, what I've seen is on the order of, the separation in space is on the order of 100, as I was saying yesterday. So
100 particles.
No, 100 is the separation between the time step, and if I'm not mistaken, you have of the order of, yes, and the delta x cube over you have of the order of 100 also in space. So that means that, let me see, let me jump to, and we will come back, because I have this number for an actual application, which is Veinan is one of those who started to do that, and that's the application I wanted to show. We will do that next, but let me jump to the number. So out of this paper, what I read is that the ratio of the time steps is of the order 100,000, and this is the volume of the macroscopic, the entire domain, versus the volume of the molecular dynamics domain is about 1,000. So you do molecular dynamics on 1,000th of the total domain. And let me tell you, this calculation, the grid is typically, they do molecular dynamics basically here and there, okay? So here they put a cycle or rectangle, which is basically 1/1000 of the total volume. The total volume is of the order 50 by 50 grid points, and the number of particles of the order of 1,000. If this tells you anything.
I was more asking how many particles do you have corresponding to one macroscopic cell in your
About
whole
50.
MV compared to the whole number of particles
I think
in your MV, because that can give us
the fluctuation.
a problem at the cell boundaries. If you have very big cells, then relatively the errors you make there won't be so big. If you say you have on the order of 50 particles in a cell, then I think the pair correlations, for example, between cells are really a problem you have to address, because 50 is not many particles.
50 in a cell is not, well, you don't put much more than that normally.
Yes, okay, but in that case you will have to care for the pair distributions also between cells, for example.
Ah, yes. Well, let's try to let's try to reconstruct it. What they do here, I really don't, this was the second part, but just to see whether we can reconstruct the figures and answer your question. What they do, in fact, that would be the region where there is a separation. Okay, that's what they do. So this would be the interface. This is fluid A, fluid B. Here you see the scalars, and here you see the velocity. They use a finite volume. And that's the region where they put molecular dynamics. Now, they tell me that you have about 2,000 particles here. If we are to trust this picture, which is maybe only cartoon, there would be thousands of particles over about 3 cells. But I cannot promise that this is quantitative, because that's the cartoon. I think it's a realistic cartoon.
It's true that there are many applications where they do
So there are many more.
different domains that live concurrently, right?
No, in their case, they insist on that. They call it underlapping. They do macroscopics everywhere, and then they put it molecular dynamics on top of the macroscopic.
I think they're really only using 3 cells across the whole cell.
On top means computational.
Oh, that could be. Oh, yeah, that could be. In fact, the macrodynamic people would just put 1 cell. They take pride at just taking 1 cell because they don't want to resolve the structure of the interface. So I think that's pretty realistic. 3, 4 cells at most. They want to minimize that. In a macroscopic calculation, principally, you want to use just 1 cell for the interface. But anyway, we will come to this, I think, probably in the second part, where I give you a specific example. Let me see if there is, I think there is still a little bit more to be said. When do we have the break, Tim?
Maybe we should break now.
Okay, let me see what comes next. Yeah, maybe we can break now, because then I will mention a little bit hydrodynamics with constraint. Sorry.
It's like 5 minutes.
Okay, let's take a break. I will move fast here because in the first place, I think the crucial part is the matching, and second, I'm not really an expert of that. I mean, in the sense that I'm afraid that these kind of things, in order to know them really deeply, you have to do them. I mean, it's not because there are many details which really matter. But anyway, just to go on with the general ideas. So we have been covering so far the the reconstruction step. Once you have reconstructed your microscopic state, of course, you have to move it in time. And, well, that's just, Verlet is just one possibility. I mean, there is really not much information into this slide, but I think the crucial point is that, and that's again general, the microsolver, so the exchange is that the microsolver gives the stress to the macro, because this is the highly valued, the added value of microphysics, and the macrosolvers in return fixes the constraint for the molecular dynamics. Constraints, there are several constraints. The simplest would be that you want the density of this system to be exactly the same which was provided by the macrosolver. But that really depends on the so-called ensemble. So you have to do molecular dynamics within a given ensemble, and for instance, this would be number, pressure, and temperature, and Simone just informs us that keeping, in fact, the dynamics of the molecules within the proper ensemble is a highly non-trivial job. Frankly speaking, I would refrain from any comment because, as I said, I'm not an expert. I have not done it firsthand, so I might say a stupid thing. But for sure, one thing that can be retained is that the molecular dynamics, as you use it in multiscale, is constrained molecular dynamics. And this idea that molecular dynamics provided the shear and the macrosolver provides the constraint is a general one. That the way you account for it really depends on it's a technical issue, but the general scheme remains. So I'm not sure I want to do that. And again, Simone is probably much more knowledgeable than me. I think that, for instance, if you want to keep the velocity as the one provided by the macrosolver, you would have to use some other type of constraint. You have to put maybe some friction. And just to say that there are different ensembles in what people call thermostated molecular dynamics, and the type of constraint can change depending on the boundary condition that you want to put at the interface. Now, one issue which seems to me was pretty hot, at least a few years ago, and is the fact that when you have the shear, and that's again a technical point, but an extremely important one. Suppose you have a situation like this, so you have a happy molecular cell where red molecule would move up here to the green position under the effect of molecular interaction. And if you do that in a cell which is sheared, it will happen that this molecule here will be out of the cell. So that implies that you have to take care of this. And suppose now that the motion of the corners, of the macroscopic motion of the cell, has this form, that the velocity along x is a function of space like that, and velocity along y is like this. This would, in fact, correspond to a situation where the macroscopic cell is rotating and shearing, depending on the value of ABC. And since the divergence of this velocity field is zero, that reflects the idea that the macroscopic fluid should be incompressible. So essentially what matters is the shear. So if there is a shear, then you have to really change the boundary condition of, that you are applying. Very often, if you are, the simplest possible boundary condition is that if you have a particle moving outside, you just put it back from the other side. And so that's exactly what you have to do here. So this would be the situation without shear. With shear, the red particle goes here, and you have to put it into a somehow, I hope I do it right, yes. This would be the northeast corner of the so-called image cell, the one which is next on the left. So basically, since you want to keep your information within this given cell, you would just reinsert the particle here, but with a different speed, because you have to take into account of the motion of the deformation, of the macro cell. And so there is an extra velocity component which depends on this matrix. Aij would be basically this matrix, A, B, C. Okay? So just to say that the fact that you are working with the constrained molecular dynamics implies that there are a number of technical changes into the dynamics. And again, just to mention, it seems that another real huge problem is that when the shear is strong, this is a mild deformation, but suppose you keep shearing, eventually you would end up with a situation where the cell is highly deformed, something like this, where one dimension becomes really much larger than the other, and under this condition, you can ruin the calculation. And so what people do, they just rezone. So if I have a largely deformed cell, every now and then you have to fix up your calculation and bring it back to this shape. And I mean, I don't go into the detail also because I don't master the details, but for sure we understand that this means that you have to reassign particles to new boxes. It's called rezoning. And that's, at least in terms of bookkeeping, is rather painful. But what is most important is the fact that by rezoning, in fact, you generate larger forces on the particles. So your system almost comes to an halt if you are not careful, because you have to make very smaller time steps. So this rezoning is really critical stage. Just to say that this subject becomes easily quite technical, and I think it's an open frontier of molecular dynamics. The macro solver is really imposing the fact that you want to make molecular dynamics aware of the environment. If the environment is nasty, it can really impose a difficult constraint on your system. So I think this is really an open frontier. Okay, I think I covered that. How to compute the shear, I don't think you want to do that. So if we spare time, I can move to another application. We'll see. But let me comment a little bit, and of course I should give credit to Weinan, who even provided me with the PowerPoint. So yeah, there is this method. It's called heterogeneous multiscale method, and Weinan make a huge point of contrasting his method with as compared to the rest of the world. I'm not sure I can convey his feeling, but what I gather is that they call it a heterogeneous multiscale method because essentially instead of overlapping, so I have a region where I do the continuum calculation. Please notice that the continuum calculation stops here. And the region where I do the microscopic calculation, and they just overlap here. From here on, the microscopic is on its own, right? Whereas here, in the heterogeneous multiscale, you have patches on molecular dynamics, and please notice that the continuum, the macroscopic calculation goes all over. So as I understand, they do the macroscopic calculation everywhere, and then, based on the macro values which I obtain on this grid point, they do the constrained molecular dynamics just in these patches. And you have fancy figure where these patches eventually move in time, so the patchy dynamics, as they call it, can be quite involved. So I'm not so sure I appreciate this point. Maybe you do, but essentially he says no matching is needed. I don't quite understand that, because in my opinion you always need some match, even though, because you still have an overlap between the macro and the micro. And they are sequenced. But anyway, the main difference is that here you do the continuum calculation everywhere. And they call it underlapping. Again, it's rather mysterious to me. But maybe you have a comment.
I might comment on that.
Yeah, please.
If you do the domain decomposition type of simulation, I think people run these two simulations in parallel. So in parallel time domains, and then you have to do a matching between the overlapping parts.
Okay.
Between the part which is between the micro representation of the part which is also in the macro simulation.
Yes. Whereas here
and probably that's what is referred to with that no matching is needed in the other method.
Okay. Today I think I forgot to repeat the questions, so I will start it now. I think the comment is that if I got it correctly, is that in this case, in the overlapping case, the macro calculation and the micro calculation go in parallel in time, right? Whereas in this case, they are sequential, okay? So I first do the macroscopic. I provide the values of the macro variables everywhere, and then on top of that, I do a serial stretch of molecular dynamics. It's called underlapping. It's a catchy word, but anyway, it seems that the vast majority, this is the way, this is more associated to the macroscopic parallel computing. People would solve different equations, what is called multiphysics, for instance. You solve, say, thermal temperature here and chemistry here, and then you have overlapping regions. So this is more in the spirit of partial differential equation. This is more in the spirit of putting the Ealing function of the microsolver just in the surgical way, so to say. So this is, that's why it's called heterogeneous, because multiscale method, because it's just done in critical spot across the domain. Anyway, so this is the application. I think we have already commented on this. This movie we have seen already. And I don't think I have much to say about the application, but let's take a look at some figures. Okay, this is our own calculation, but I only use it to illustrate the idea that, in fact, in the region where you have the interface, there are pretty complicated things taking place. In fact, you generate sort of dissipative structure, vortices, and for sure the velocity here cannot be zero. And one mechanism by which the fluid arranges itself so that the interface can move is by generating rolls. So it's just like skating somehow. But nobody really knows. We challenge, in fact, the experiments to do that, but it's very hard to visualize this.
Is that truly two-dimensional, or are we seeing a projection?
The calculation is two-dimensional, but I think in microfluidics, two-dimensional is not too bad, because they are really, very often, if you see their chips, the chips they design, they are really almost like wafers. Yes. Let me see if there is anything specific. I would say I wanted to see whether there are some data regarding the numbers, actually. Well, I don't think we need much comments here. Okay, they do the sampling region. Okay, the way they keep, for instance, here this will be the region where they do molecular dynamics, but for practical reason they extend it in order to have a buffer between the macro domain and the micro domain. And in order to keep the particle within the buffer, they use a repulsive force here. So if a particle gets here, it's repelled, which is, again, something I do not quite understand, because it seems to me that you are really changing the physics of your problem. So I don't really like this very much. And the sampling region is, in fact, the important one, where you would pick up, in fact, the stress tensor and give it to the macro calculation. So the sampling region is where the valuable information is plugged into the macro solver. And as you see, is really a very thin region, which is appropriate, because continuum is probably good almost everywhere except the critical region. So I don't know whether you have questions. On my side, I'm not so sure that I need to comment much more. So these were the figures we were discussing. Yes, I can comment on this. You remember I mentioned the Heracles paradox. The Heracles paradox tells you that a continuum would have a singularity in the triple point here. And of course, this singularity cannot exist in nature. And if you run a full molecular dynamics simulation, this would be the shear as a function of this coordinate up to the mid, so that this peak would be this location. And of course, it's not infinite. There is a sharp peak, but it's, of course, finite value. So as usual, the way you validate multi-scale technology is just to compare with the full microscopic calculation. So you run a full molecular dynamics, and that's what you get. And when you run the multi-scale method, I don't wear my glasses, but essentially to validate, to prove that their method is not generating uncontrolled errors, they prove you compare the critical quantity, which in this case is basically the shear. So judging from this picture, I would say that the job is well done. And of course, it is done at a small, very small fraction of, I think here the ratio of the two calculations would be 1,000 at least. So by you do some mistakes, because I mean they are not exactly the same, but by and large you would say you are pretty happy if you can get the red curve at a price of 1,000 or even less than the blue curve. That's really the spirit of multiscale. So you tolerate errors, but at least you compute things which would be otherwise unaffordable. I'm sure you appreciate that the limit of molecular dynamics, if you have to do a full channel, even a microchannel in molecular dynamics, there is no way you can do it. I mean, especially the time scale would be totally out of reach. By doing multiscale, you can hope to address larger channels and get closer to experimental conditions. I don't think I have much more to say. If there are no comments on that, I would just summarize the main point we made during this lecture. So we started, I hope I get them in the right sequence. So this type of calculation, typically macro-nanofluidics are important whenever constitutive relations become questionable, as they do become questionable for complex nano and microfluidics. I think we have commented on the fact that dissipation is really tightly connected to the notion of non-equilibrium, and non-equilibrium is associated with strong gradients than small objects. Dense fluids involve two-body correlation and more, as we have learned today, so sampling, the reconstruction step in this case is really highly delicate. I mean, it's really not trivial at all. For a rarefied gas, it is much easier. I mean, people do not have much of a trouble. I mean, so liquids are really much more complicated. Okay. I think, yeah, and we discussed the fact that the micro gives the stresses, which is the flux of momentum, and the macro fixes the constraint. This we have commented, and also this is highly technical but extremely important, that doing constrained molecular dynamics with deformable boxes is really an open technical issue. So unless you have questions, I think for once I'm ahead of time. I really don't know what to do, but I could start something on a subject which might be of you. Tim told me that you wanted to know something about turbulence. So by the way, any question to this point? I think no. I'm not so sure whether we can do the following. I can introduce the main notion regarding turbulence, the way people model it, and tomorrow we'll go into some detail. So this is an old talk. I'll work with Udong Chen, you know, because he gave a colloquium a few months ago, Nexa Corporation. This is what we did a few years ago with Steve Orszag at Yale. It's really different, pretty different subject and pretty different philosophy, but I think there are some interesting points to this subject too. So now, in the first place, we are working just with a single level. We are not combining anything, but we are working just at the level. So remember, we have Navier-Stokes continuum, we have Boltzmann kinetic theory, and we have atomistic dynamics. This is the classical picture. And then we will have, tomorrow we will have also some quantum mechanics. So the problem we are addressing here is turbulence, which is one of them. Possibly it's often hailed as the last unsolved problem of classical mechanics. It's maybe a big word, but it's not far from the truth. And that's a typical problem where people would immediately associate turbulence with Navier-Stokes equation. And we took a rather odd angle of attack to this problem. We insisted that we would rather use tools from kinetic theory, the lattice Boltzmann we discussed yesterday, to address turbulence. And that was not easy to, I mean, the community reacted somehow in a rather strong way to this idea. Now, turbulence is really long-standing, and our co-citizen Leonardo da Vinci was busy with turbulence many years ago, 500 years ago. And this is a picture from Leonardo, and with all vortices going up and down. And it is, in fact, an old problem, because these equations, the Navier-Stokes equation, which you have seen many times, are known for more than 150 years. And I don't know in this country, but in Italy, until recently at least, there were highly respected physicists, especially in the high energy hand, saying that if you know the equation, the physics is dead, which I think is a very bad prejudice. We are, I think, standing just on the opposite side. The physics is in the solution of the equation. So in that sense, fluid dynamics is just a boring thing to do, right? And I think in this country is probably not completely different, because I think string theory has basically expelled fluid dynamics from the, that's what I heard, I don't know, from the physics department. But anyway, but turbulence nonetheless keeps a P degree, because it's really considered an intellectual challenge in the sense that you don't really know how to characterize the, even from a statistical point of view, the distribution of a turbulent field in space and time, even though the equations are pretty well known. Now, why is that so? The beauty of turbulence is that the complexity is really can be traced to just a single parameter for an incompressible fluid like this. And this parameter is so-called Reynolds number. So what is the Reynolds number? The Reynolds number is, take a car, would be the speed of your car, say, I don't know, 60 miles an hour, times the length of your car over the viscosity. I might have asked this question again here. I'm not so sure whether it was here in Italy. But this Reynolds number is a huge number. The numbers basically measure the relative weight of inertia, kinetic energy, versus dissipation. Okay? So, and I tend to ask, in fact, whether people who are not used to deal with fluids, whether you have a sense for what this number could be. So it's, for a field theorist, Reynolds is the coupling strength. You see, it's basically how strong the nonlinearity is. Now, if I give you a car, would you have an idea? We have been discussing molecular dynamics. Let's move to the macro. I give you 3 chances, nonetheless. I give you 10 to minus 2, 10, and 10 to 6. Which one would you pick up? It's a simple test. A moving car. The car has to move. If it's in your garage, it's 0. A car, say, I would say in Europeans are 100 kilometers an hour. Your car is supposed not to be a Cadillac, even if it's a car, it wouldn't change. But say 1 meter, and this is the viscosity. Viscosity of air is 10 to the minus 6 square meter per second. I give you a big clue at this point. So, and I give you three values. 10 to minus 1, 10, 10 to 6. So very small.
10 to 6.
10 to 6. You knew it in advance.
I would say, of the order of 1,000, but it's actually closer to million.
A faucet is 1,000. Water faucet is 1,000. So a standard car would be almost 10 to 7.
Well, we drive like an Italian.
Then, well, you know why? I think we can, it's easy, because you remember we have been talking about this abstract gap, length to length. Reynolds is a gap. It's a gap between molecules and macroscopic world. You remember that the viscosity I told is a length, mean free path actually. I think I called it lambda times a thermal speed, yeah? And the thermal speed is kT over m. Okay? Now, let's write the viscosity this way. We can afford it. The math is really simple. So Reynolds will be UL over V thermal mean free path, right? Now, if we are driving even like even a Ferrari, actually, a Ferrari would move at the speed of the molecules in this room. 300 meters per second. No, how much? Let's see. Oh. No, I'm exaggerating. 10 meters per second is 36 kilometers an hour. Oh, almost. So for a Ferrari, this number is 1/3. Am I right? So 10 meters per second is 36 kilometers per hour. So a Ferrari moves 100 meters per second. So it's much slower than a molecule, but so the Mach number, this is called Mach number, essentially. Because for an ideal gas, the thermal speed is basically the sound speed. So let's say that this is 1. So we make the Ferrari even faster. But still, the reason why Reynolds is so big is because here there is really no comparison, because this is 1 meter, and the mean free path in air is 1 micron, even less. That's where you get the 1 million. You're really measuring the Ferrari with a stick, which is the particle mean free path. You remember the picture I showed you before, when I had the density like this and I had the molecule colliding, and I said that lambda has to be much smaller than L. Okay? So for a good fluid, and so turbulence is really for macroscopic fluids, given that the Mach number is of the order 1. I mean, if you move in a porous medium, Mach will be 10 to minus 3. But for a macroscopic object, let's say that this is 1. So the Reynolds number is big because I'm measuring my Ferrari with the mean free path of the molecules. So that's the space gap that you have in turbulence. And alas, this is also the coupling stress. So that means that your nonlinear kinetic energy is 1 million times bigger than dissipation. So you say, good, I forget about dissipation. Deadly mistake. If you forget about dissipation, you would not acknowledge the fact that you need gas to move your car. And you definitely know that you need gas. So the trick is that dissipation is small, but not because it doesn't matter, because it's hyperlocalized. Typically, you dissipate all of your energy near the wall of your Ferrari. And this would be maybe 1 millimeter or a few millimeters. That's where everything takes place. And that's, I would say, a general rule of nonlinear complex system. You remember the movie Contact? Okay, so the closing statement in Contact is the, how is called the lady? Judy Foster. And she has a name in the movie, but I don't know. And Judy Foster is asked by some guy, is there intelligent life in the universe? And she says, well, we don't know, but you know, it would be a big waste if there were none. We don't know, but as a matter of fact, when it comes to complex systems really do waste space. I mean, because everything takes place in tiny portions of phase space. So based on this argument, I'm not so sure that the comment by Jodie Foster was catching the truth. It is typical of complex systems to do all of the important things in very, very tiny corner. And the more you make Reynolds bigger, the tinier will be the region where dissipation takes place. But dissipation will not disappear. So a high Reynolds fluid is not an ideal fluid. It's an ideal fluid almost everywhere, but not near the wall. And near the wall, the wall will change. And if you forget about the wall, you have lost the physics. So that's why, and I already gave you a clue of why it's so difficult to solve these problems on a computer, because you have to resolve lengths which becomes tinier and tinier and tinier. So that's the problem of turbulence, in a nutshell, of course. We can be more quantitative, and that's still, I would say, the major result in turbulence, which dates back to Kolmogorov 60 years ago. Based on purely dimensional argument that we could easily replicate in a few minutes, he was able to derive the value of the so-called Kolmogorov dissipative length. This is, if you want, the size of the smallest vortex, in fact, turbulent structure that you can have in a fluid, given the size of the macroscopic object. So this will be the size of your car, and given the Reynolds. So as you see, it's not Reynolds power 1. So the Kolmogorov length is kind of bigger than mean free path, but still the separation is huge. Okay? So if I have Reynolds 10,000, which is slightly more than a water faucet in our kitchen, we will still have a separation of 3 orders of magnitude between the size of the faucet and the smallest eddies, which still contain energy. So separation is huge. And when you do the count of degrees of freedom, and you want to solve a three-dimensional flow, and eventually I should add time here, so this should be power 4. But let's stay with space. If I want to solve a cube of size side L, capital L, the number of degrees of freedom grows with power 9 to 4. So that means that a car, 10 to 6, will give you, I wrote it here, a car will give me 10 to power 14. Geophysical problems, say hurricanes and things like this, easily go into the 10 to the 20 degrees of freedom. That's why there is no, I mean, a faucet would basically fill up our most powerful machine as we know them today. Cars, no way you can design a car just by resolving all the length, the dynamical length and geophysical phenomena out of question. So this is the reason why people cannot do what is called direct numerical simulation. Direct means I take the equation and I solve it all the way. I try to resolve all the dynamical speeds, the dynamical, scale which I have in my problem. And that's again the same picture. So, and there is more to say because here is the usual representation is that you put the amount of energy that you have as a function of the wave number, which is just the inverse length. So here we would have the large scale eddies, and here we would have the small ones. And you remember I mentioned the cascade. Due to the term U grad U, I have a large eddy. The large eddy would break down in smaller eddy, and there would be a continuum cascade. And Kolmogorov was able to capture the exponent of this spectrum, which is minus 5/3. The important thing is that this spectrum is continuum. And we commented about that. That is basically the reason why it's very hard to do any scale separation. So essentially, this motivates the so-called turbulence modeling activity, which really keeps engineers busy for, I would say, at least 40 years now. And there are many approaches. The first approach is that, okay, this is a spectrum that you have to resolve. Here is called dissipative, but this is just the Kolmogorov length. Okay, so total versus the, and this is the spectrum of the size. Eddy means vortex, basically. So direct numerical simulation is, I take it the macho way. I have a computer big enough, I can put my resolution down to the Kolmogorov length, and I solve it all the way. But you can't do that. You can do that for a water faucet at best. Okay? Of course, people do numerical simulation, direct numerical simulation a great deal, but in general, not for, it's not for engineering, practical engineering purposes. Second approach is large eddy simulation, where, as the name suggests, you would just simulate the largest eddy. So you have a grid size, okay, and you say, okay, from the total length down to my grid size, I can afford, so I do much less. And from there on, I have to invent some model, which is a way of reconstructing information in a totally different guise. But here you have somehow to make a guess on what the effect of the small eddies, since the spectrum is continuous, the small eddies here will have nonetheless an effect here and there. It will damp down, but you cannot neglect it. If you neglect it, you miss the physics. So the green part is the part where, again, you have to reconstruct. You don't do sampling, as we saw for molecular dynamics, but you do similar kind of operation. And in general, at least in the engineering community, the way it was taken is the following. That this is Steve Orsag, and he calls it very large eddy simulation because it says, of course, the idea is always to apply the principle of least computing. You want to make the red strip as small as possible. You want to compute the least amount of scales as possible. And, well, this is getting a little bit too technical, but essentially the point is that if you are smart enough, in fact, you can have theories which allow you to guess the behavior of much larger eddies than a conventional simulation would do. So that implies essentially a renormalization group kind of argument. Is not really easy, but essentially the point is that, maybe I can convey this point. When I'm here, I'm totally non-universal. The large eddies will know about the geometry of your car, right? As you move down the line, they will become not only smaller and smaller, but more isotropic and isotropic because they tend to forget about the geometry. So they get sort of universality. And the idea is that by the time you're here, you have forgotten that you came from a car or from an airplane. And there are statistically universal laws, and those are the ones acknowledged by Kolmogorov. Now, the idea of Horsag is that for some reason, you can have theories which describe not only the totally universal eddies, but also some eddies which are still a little bit, as it says, anisotropic. So that would be too involved. It's just to say that you can have some statistical mechanics argument which allow you to describe eddies which are non-totally universal, and if you're able to do that, then you can reduce the amount of computation. And of course, there are also totally, that's the totally, if you want, this is the hard way, the rigorous approach. I want to derive the dynamic equation for the correlation from scratch. I don't want to compute anything. So that would be the hard statistical. So this is full simulation, full theory. I must say that many engineers, RANS is a terrible. I mean, the set of equations that you have with RANS is just horrible. I mean, it's tensors, the nonlinear equation for high-order tensor, and not only they are difficult to solve in the domain, but the boundary conditions for this equation are really, so these equations are very unstable. I mean, it's really a nightmare to work with. It's again the closure problem we were discussing, and I don't give you the equation, but the philosophy is really there. And that hasn't been, I mean, in some mechanical engineering department, they would kill me if I say this, but I would say that for the last 40 years, I mean, the progress has been very, 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 very slow. So it's, I would say nowadays the mainstream is more or less here, and okay, and EXA and the people here using the lattice Boltzmann for turbulence are basically trying to propel this idea of very large eddy simulation. So somehow the current trends are, I would say 90% of the people are here, and the people who are buying into the lattice Boltzmann approach are basically on the VLS. So tomorrow I think I can give you a little bit more of detail, but I hope you appreciate that this, although the methodology and the physics are totally different as compared to the microfluid, still in any field where you have to deal with a complex problem, you have this mixture of total simulation, total statistical mechanics, but probably the solution is somewhere in between. And the solution will inevitably imply some guesswork. No matter how, but it will always be like that. So I think for today, we can close it here. Tomorrow I can go on with a little bit more details. And then I will go into something where I pray that Tim is around because it is his subject, which I give only for completeness because it's the only example I know where 3 levels have been coupled. So it's very remarkable. The so-called MAD. What is MAD? Molecular?
Multiscale, atomistic,
Atomistic.
dynamics.
Okay. So I will talk about something I don't know. Very good. Thank you for being here.